All right, let's just jump right in. We're about to go on a hunt for maybe the most elusive things in the entire universe. Black holes. I mean, these are absolute monsters of gravity, right? They shape entire galaxies. But, and this is the big but, you can't see them. They are completely invisible.
So take a look at this. These are these massive, colossal radio jets just blasting out from a galaxy called Cygnus A, and they stretch for tens of thousands of light years. It's just incredible. And the engine that's powering this whole spectacle, well, we can't see it. It's a supermassive black hole. We're talking about one of the most energetic things we've ever found in the universe.
And that right there, that's the central mystery we're tackling. I mean, think about it. If a black hole literally swallows everything, even light, how in the world do you prove one is actually there? It's like the ultimate cosmic detective story, you know? And the universe? Well, it's left clues all over the place.
So, to crack this case, first things first, we need to get a really good handle on what exactly we're looking for and why our target is so incredibly good at hiding.
Okay, so here's the official rap sheet on our culprit. A black hole is basically what happens when gravity just wins. Completely. You have a massive star that collapses under its own weight, crushing itself down into this point of unbelievable density. And its gravity gets so intense that it creates a boundary around it. We call it the event horizon. And once you cross that, nothing gets out.
So this is the key, the absolute key to the whole hunt. We don't look for the black hole itself. We can't. Instead, we look for the chaos it leaves behind. It's all about hunting for its gravitational fingerprint on all the stuff, the stars, the gas, that just happens to get a little too close.
All right, let's start small, or, relatively small. We'll start with the stellar mass black holes. Think of these as the ghosts of huge dead stars. And it turns out they have a favorite place to hang out.
Now get this, something like 2/3 of all stars are actually in pairs. They're binary systems orbiting each other. And this setup, it creates the absolute perfect crime scene. Because when one of those stars dies and collapses into a black hole, it's not alone. It has a partner, a witness that it just can't hide from.
And this is where it all goes down. The black hole's gravity is so strong, it starts literally ripping gas off its partner star. But the material doesn't just fall straight in. Nope, it spirals inward, forming this spinning, superheated platter we call an accretion disk, and the friction in that disk heats the gas up to millions of degrees, making it glow like crazy in X-ray light. And that is something our space telescopes can definitely see. But here's the thing, just seeing a bright spot of X-rays, that's only our first lead. It's not a slam dunk. Why? Because other things like super dense neutron stars can also make these accretion disks. So to really nail our suspect, to get a conviction, we have to prove it's massive enough to be a black hole. We literally have to weigh the ghost.
And this is how they do it. It's so clever. For a minute, we just forget about the X-rays, and we focus all our attention on the other star, the survivor. As it orbits its invisible partner, it gets pulled towards us and away from us, over and over. This creates a tiny wobble in the starlight that we can measure. And that wobble tells us everything, exactly how fast the star is moving and how long it takes to go around.
So, with that wobble data and some basic physics, we can calculate the mass of the invisible partner. And here it is, the clincher. If that unseen object weighs in at more than 3 times the mass of our own sun, well, it's just too heavy to be a neutron star. It's too heavy to be anything else we know of. It has to be a black hole. Case closed.
Okay, so we've cracked the case of the smaller culprits, the stellar mass ones. Now it's time to go big. We're scaling up the hunt to go after the real kingpins of the cosmos, the supermassive black holes that are lurking right in the heart of pretty much every galaxy, including our own.
And when I say big, the scale is just, it's hard to even wrap your head around. A stellar black hole might be what, 10 times the mass of the sun? A supermassive one can be millions or even billions of times more massive. We're not just talking about a difference in size here. This is a whole different class of monster.
You know, finding the one at the center of our own galaxy, the Milky Way, that was an absolutely epic job of cosmic surveillance. The basic idea was the same. Watch how stuff moves around something you can't see. But instead of just one star, astronomers had to track the super precise movements of dozens of stars for decades. And this is the smoking gun. Each one of those lines is the actual orbit of a star right at the heart of our galaxy. Look at them. They are whipping around a single empty point in space at just unbelievable speeds. There's only one thing that can explain this, a single supercompact object with a mass of 3.7 million suns. And that is Sagittarius A star, our galaxy's very own supermassive black hole. So, there we have it. We figured out how to find something that's totally black. But, the universe always has one more twist, one more mind-bending surprise up its sleeve. And it's this. It turns out black holes aren't forever, and they're not even perfectly black. In a way, they glow.
This wild idea is called Hawking radiation, named, of course, after the one and only Stephen Hawking. What he realized was that if you take Einstein's theory of gravity and you mix it with the bizarre rules of quantum mechanics, right there at the edge of a black hole, something totally unexpected happens. Black holes can actually leak. Very, very slowly, they leak energy back out into space.
Okay, so here's the simplified version. All through what we think of as empty space, pairs of virtual particles are constantly popping in and out of existence. It's a quantum thing. Now imagine this happens right on the razor's edge of the event horizon. One particle might fall in, but the other one just barely escapes. That escaping particle becomes real, and it flies off carrying a little bit of energy with it. So, where did that energy come from? Well, the black hole has to pay the bill. It pays by losing a tiny, tiny fraction of its own mass.
Now, over huge, immense timescales, this actually adds up. And here's the crazy part. As the black hole loses mass, it gets hotter. And because it's hotter, it radiates away even faster. It's a runaway process. This means that every single black hole in the universe is basically on a slow burn fuse, and it's destined to eventually evaporate in a final brilliant flash of energy.
Now, before you get too excited, don't hold your breath. For a black hole that's just the mass of our sun, this whole evaporation process would take, well, way, way longer than the entire age of the universe so far. It's an unimaginable amount of time. So no, we're never going to see this happen. But the physics is crystal clear. Nothing, not even a black hole, truly lasts forever.
And that kind of leaves us with one final big thought. These invisible giants, they're not just cosmic vacuum cleaners. They're like these incredible laboratories, pushing the laws of physics to the absolute breaking point. They hold the clues to gravity, to quantum mechanics, maybe even to the ultimate fate of the whole universe. So the real question isn't just how we find them. It's what other secrets will they teach us before they finally, eventually, fade away.